So guys, you already saw them on the screen. Here, Petar, Rousev, and Lyubomir Nedyalkov. And enjoy and have fun.
Okay. Hello, everyone, and thank you for joining us today. In our session, we will show how SRE ensure reliability and stability of productive systems in ever-evolving landscape, and how AI agents help SREs to work smarter and stay resilient. At the end, we will wrap up with a live demo that will showcase the capabilities. Our journey starts with a brief overview of our global site reliability engineering presence and structure. Site reliability engineering is a discipline that combines software engineering and system engineering practices in order to ensure the availability, performance, and scalability of production systems. Our SRE organization operates across 5 strategically distributed locations, and in total, we are 12 SRE teams covering 50 productive services. This global distribution is intentional. It allows us to adopt the follow-the-sun support model, which ensures our continuous coverage on these productive services while maintaining sustainable on-call practices for our teams. This structure not only enhances our response time, but also contributes to our broader objective to deliver reliable, high-quality services at scale. Now that we know what SRE is, we'll walk you through some technical details so the demo at the end doesn't look like magic. Let's start with the big picture, which is standing behind the SRE Copilot. It's a network of intelligent agents that can observe, analyze, and act, and together with that, fully integrated with the entire ecosystem. At the core, we have these agents which mirror the expertise and workflows of all SRE teams which we have part of our organization. They replicate human decision making and responsibilities, but deliver it with speed, precision, and scale. To understand how it works, let's take a closer look at what defines an agent. Each one is powered by 3 core components. The first one is the context. This is the intelligent profile that defines the agent's capabilities and its operational boundaries. Through the context, each agent knows what domain or services it's responsible for, what issues it typically solves, and even its own personality and operating style, shaped by the practices and characteristics of a real SRE team. This contextual awareness allows the agents to act with precision. They know when to take the lead, when to support other agents, and how to align with the larger incident response effort. The second component is the toolset. This is the operational interface that gives each agent the ability to analyze real-time telemetry and propose remediation steps when it's needed. Agents are able to propose such kind of fixes or steps which can resolve a particular issue, but these proposals should be and must be confirmed from a real engineer because each of these actions are integrated in the so-called human-in-the-loop process. This keeps a balance between autonomy and oversight and ensures fast response with the full accountability. And finally, the knowledge base. This is the rich blend of architectural models, past incident data, dependency graphs, and procedural runbooks that each agent can draw data in order to make informed decisions. And now, we will explore how the Copilot managed this vast mix of data.
In SRE, we actually always had knowledge, tons of it in fact. The documents, runbook, everything it was there. But there was a problem. These documents, they were unstructured, scattered. It was one big mess, to be honest. And one of our focuses with the SRE Copilot was to make something actionable from this mess. So we are introducing a separated component, so-called the data loader. And he has only one job, to provide all of the data into a single source of truth. Let's see how that's done, to check the whole picture. Here, we have the data loader who cares about the ingestion, then the agent queries the information, and we need a place where to store this information. We have a knowledge graph in a hybrid setup with vector embeddings. But that was not the picture all the time. In the beginning, we were using a simple vector database. And all previously mentioned documents, we were creating embeddings of them, storing them in the vector database so the agent could query the information and search them by context and similarity. But this had a problem. We wanted, as Petar already said, we have 51 services. And each one of them is deployed across 40 different landscapes in all major IaaS providers, including one of our own. You can imagine the complexity and the amount of data which we had and we need to handle. And here the knowledge graph comes in. The knowledge graph provides us with the structure about the data. In our hybrid setup, inside the actual graph nodes, we are storing the embeddings, while the edges are semantically connected, so it gives us the relationship between the documents and the nodes. Like that, our agents can't only just query the information, but also see the whole picture and all of the connections in the relationship with them. If we go back to the slide, now let's focus in the next part, and that will be the ingestion. How do we actually bring the data to the knowledge graph? Here, it's simple. We have a few steps. The first one, obviously, we are collecting all of the documents from different data sources, from everywhere almost. And here also the caching mechanism happens. If a document was already collected, create a hash based on the stored in the cache, then so we don't proceed any further with the next steps. As the next steps are a little bit more of, let's say, expensive and so on. And the next part is we actually create the embeddings of the documents. Here, in a multi-threaded way, while we split the documents in batches, we process them, we create the embeddings, so it can be faster and smarter. And then finally, but not on final place, we do the metadata enrichment. What does that mean? Using a large language model, we extract the title of the document based on the content, and the 5 most similar questions which could be based still on the content of the document itself. That's from the ingestion process. Then we actually have the query. The query, I can say that it's one of the simplest things from the user perspective. You just go to the Copilot UI and using a natural language, just queries the knowledge base and receive the needed information based on the knowledge base. That's from the query. And if we go back to the...
And here, to have a better understanding what we mean by documents, let's take a look at this example runbooks. These are kind of a blueprints. But imagine the scale and the amount of data which our engineers need to work. Because as we said at the beginning, we cover 50 productive services. And these services are deployed across all major IaaS providers. So imagine how much information we need in order to be able to react on a particular issues which they occur, or when we are put in a call to resolve an outage, for example, at 3 at the night, when each and every minute actually matter. So these RAM books actually results in this picture. This is the knowledge graph, actually, example of a knowledge graph which is built on these blueprint RAM books. All the nodes here, as Lyubomir explained, are created containing embedded data based on the RAM book in their structure, and the edges are defining the semantic connections between all the nodes created. So now let's proceed with the live demo, where actually we will walk you through the entire process, how the entire knowledge graph looks, how we can query for data, and what are the capabilities of the agents which are stepping on this knowledge graph. So let me switch the screen and start. First, I would like to show the knowledge graph in the database explorer. It's not so nice as in the picture which it's not visible there. How to switch the screen? Probably I need to. Give me a second just to switch the proper screen. Okay, it's visible. So as I said, this is the database explorer which we have in hand, and the knowledge graph which we are already built, stepping actually exactly on this example RAM books, looks like this. It looks a bit scary, but in the essence, if we zoom in, each of the nodes are representing some particular piece of data which we have defined in these RAM books. And if we zoom a bit further here, we can see that each of the edges represent particular semantic connection between these nodes. And basically, I cannot expand the whole graph because it will become even scarier. So for the next part, we have one simple application where we can take a look at the graph in a more convenient form. So let's take a look here. We have a RAM book here as a node, which is connected to almost each and every node in this schema. So this RAM book have 8 connections, for example, and one of these connections is what is the escalation path when a particular issue occurs. This basically means which teams our engineers needs to pull in case they identify such need. There are, for example, diagnosis and remediation steps related to the dependencies of the particular service, and a lot more. So having the graph already created for us, because the most expensive operation actually is to prepare the data and build the graph stepping on it. That part I unfortunately cannot demonstrate right now because it takes some time, and that's why we prepared it before the session. But we are able right now to query the graph, and using particularly this hybrid mode of querying the graph, including including operations which are not only traversing the graph based on the semantic connections which we already presented, but also comparing the embeddings which are basically enrich the context with which we can able actually to work later, and the agents stepping on that. So for example, for that purpose, I will execute this particular query. These questions, which we see here, are actually generated as part of the graph creation. Lyubomir already mentioned that. As part of the metadata enrichment and the content of each and every particular node, actually we generate at least 5 most relevant questions which this particular piece of data can satisfy. So for the example, I will use this particular query. And right now, the process of extracting the data already started. While it's executing, let's take a look actually what's happening under the hood. So here, you see, actually, is it necessary to zoom a bit? Probably yes. I will zoom it in. Is it okay now? Okay, so we saw that as a first step, it was executed a so-called HANA cipher query retriever. So what this basically means is with the help of a large language model and the specifics of the open cipher specification, we are generating an open cipher query which is intended to resolve our request, whether it's a question or whatever prompt we push through the agents. Right now, actually, we don't have agent in the picture. Right now, we just have a large language model, and through this, actually, we are querying the knowledge graph. So let's see what happened as a next step. There were a chain executed. And as part of this chain, we have, as I explained, HANA cipher query retriever with the already created open cipher script. And then we see here that we executed also a vector retrieval, stepping on the already provided data from the previous step. What this basically means, we can what's happening under the hood actually through the cipher query, we receive a subgraph of the larger picture, and this subgraph serves the vector retrieval in order to provide us actually the context, the data which is really matters. So at the end, at the step where we are refining the results which we received from both retrievers, we can see that based on our question, this is the response which we receive, stepping on the context which were previously created for us. And finally, that's the, let's see what actually were the actual response here. So this is actually explaining what is this what's talking about when we mention this particular runbook. So let's proceed further. What we, and maybe first summarize a bit. What we did right now is querying the knowledge graph, but without having any agentic approach. It's a simple query, which can be done with whatever large language model we decide to use. But right now, at the next step of the demo, we will see how the agents use this data and how stepping on these runbooks, because in this particular runbooks, we included some data. Of course, we don't want to break some productive systems and make our colleagues' life harder during the conference, going to resolve some issues. So for that purpose, what we did is we created a simple demo application. This demo application has a dependency to a database. And this database, of course, is PostgreSQL. And what we are going to, in this runbooks, actually, we explained what is these dependencies between the components of the system, and what remediation steps can be taken in order to remediate particular issues. So let's see this in action. This is the interface of our Copilot. As we explained briefly at the beginning, it's consisting of 12 agents as of now, 12 agents as of now, and each of these agents is specialized with the context of a particular team which we have in the organization. It's able to provide information, propose actions which can resolve real issues, analyze logs, and whatever process is relevant in order to support the larger incident response effort. So let's navigate directly to our demo agent here. Let me first just really quickly to refresh my session here. And here is the demo agent. So what I'm going to ask right now is, what is the current state of the demo application? And let's see what will be the response. In the meantime, as you can see here, something pretty important happened when I send the response, send the request. And this is exactly the message were anonymized. This basically means that everything which goes through this system passes through the anonymization, and in this way, actually, we ensure no sensitive data can be forwarded to the large language model which we are using under the hood. And this is something pretty crucial and important when we speak about using large language models and AI responsibly, and having in mind the context in which actually we are using AI here and the agentic approach. So in the meantime, our agent responded. And luckily, our demo application is up and running. But we need to break it right now. So for that purpose, I will navigate to the cockpit from where actually we manage our services and assets in SAP. So here is the demo application, and as the agent showed us, it's up and running and there is no issue with it. And let's navigate to the configurations of the databases. You see here we have a one key configured, which key is used from the application in order to be able to authenticate and establish session with the PostgreSQL instance. What I'm going to do right now is go and directly delete this key. And we can imagine this scenario. This is a simple example, but such issues happen. Wrong configuration, misconfiguration, human error, and etc. Such issues can happen even in the reality, and I believe that such kind of issues were part of your experience also. So the key were deleted. Right now, what I'm going to, I would simply check the status again. So here there is nothing prepared. Actually, I'm using whatever I come with as a prompt to the agent. So actually, I hope that it will work as expected, but let's see. And luckily, it is working. So we have state down of the application. And here, we can also see what the agent is doing, observing its chain of thought. Not only through the observability stack, which I showed you previously, but also the user, from the user perspective, you are able to track each and every step which the agent takes in order to satisfy our requirement. So the application is down. What we are going to do now? Usually, in such scenarios, first thing which we do is go and check the application logs. What's happening? One of the steps, of course, it's not the most prominent, but one of the steps will be why not? I would like to go and check the logs. And usually this means go to a dashboard, find the particular instance, find the proper filter, and etc., and etc. A lot of steps. But with the Copilot and this particular agent, I'm simply able to trigger a command. And this brings me an interface from which I can trigger a log collection, but not only providing me the particular logs of the application, but also execute a thorough analysis of these logs and provide me the most prominent issues and errors observed from this huge amount of logs. And you'll see it right now. Let's trigger it. And the logs are here. Actually, this is extracting logs from our cloud instance. It's not something which is currently I'm showcasing from my machine or whatever it is. So you see here, the logs are provided to me, and if I want, I can query manually the logs. Of course, the issue here is pretty much obvious when I see here the logs, but let's see what the analysis will bring to me, what insights it will provide to me in order to be able to remediate this issue. And while waiting, imagine that we are in a call with Lyubomir, and we are working together on this issue. I can simply go here and share the thread with him, and he can see in real time what I'm actually doing and what insights the agent brings. In the meantime, the analysis finished, and the most prominent one is here. Database authentication failure spike. So we see here the details and how often this issue occurred. And of course, this is the actual issue. What will be the next step? Usually I need to go and manually recreate this key, but instead I'm going to do the following. I will simply ask the agent, fix it for me. What will happen now? Let's see. What will be the response of the agent? And it is simply fix it for me. It's not do that or do this. A simple prompt. And here it is. It's proposing to me to execute a recommended action. And why it's aware which recommended action to execute? Because it queried the knowledge graph, and it knows for this particular kind of issues, this is the action which needs to be taken. And it's waiting for my confirmation. I confirm this. As I said, such kind of actions are always in the human-in-the-loop process. For now. Probably in the future it will be absolutely autonomous, but for now we need to have this insurance, so to say. And right now the recommended action is being executed. The agent is polling the status right now. What's happening with the execution of this recommended action? And luckily at the end, our application will be again in the up and running state, but let's say, and yes, our application were recovered with 3 simple prompts to the agent, which we have part of our ecosystem. Again, let me wind back a bit. Imagine such kind of scenarios on a scale which we mentioned, 50 services on all IaaS providers, including our own. So the application is up and running. Let's see for additional evidence here in the cockpit again. I will refresh the page. Let's see whether the key were recreated for me. And yes, the key is here. So with that, I would like to thank you for your time and attention. We have 1 more minute for some questions, but of course, after the session, me and Lyubomir will be available if there are some questions or discussions happen in the meantime. So thank you very much.
Thank you.
There is a question over there, but Yes, we have only 1 minute, guys, for questions. So,
Yeah, hi. Just wanted to ask really quick, you mentioned that it's an LLM that extracts metadata from the documents, like, the title and the most relevant questions. But is it also an LLM which decides how to connect the graph itself? So which document to connect to which in your knowledge graph? Or is this something that you do manually as well?
Actually, we don't have any manual step here.
Okay.
Everything is handled by LLM, but with precise guardrails. And it's not about prompt. Sorry, it's not about prompt engineering. It's actually really establishing particular guardrails. When actually because we are using OpenCipher specification in order to be able to traverse and also generate semantically connected nodes. And this is a pipeline, actually, pipeline of steps which are being executed, some of which in parallel, in a multi-threaded fashion, and some of which we needs to wait for the previous steps to finish. So, yes, this is the way how we do it, but we do not write the OpenCipher manually. That's the trick here.
well, okay, I see that there are other questions, but we don't have time. Sorry.
Yeah, I have an answer for you. We have almost 3 or 4 real success stories which are part of exact scenario which I mentioned here. Actually, Lyubomir's team were able to identify and provide insights to the service team for an issue which occurred in a matter of probably a minute or something like that.
Less than a minute.
And it is in a productive system, exactly utilizing this particular case which I showcase now.
Okay, so we don't have time and we don't have break,
Thank
so
you.
thanks. And if you have questions, we do not have a speaker room, so we have like the corridor hall, so you can just catch them and ask them whatever you want.
Yeah, thank you.
Thank you.
Okay, guys.